aim of my presentation today is to give you a sort of an overview of the tidal stream market, give you some insights into the potential for the UK. Also concentrate very briefly on some of the key technical challenges facing the industry, and talk briefly about some of the technologies that have been under development. And this is tidal, not wave. So I want to keep it quite specifically on tidal. And then finally, if I have enough time, just give you a brief taste of what my new technology company is doing. Well, the first thing is really sort of what qualifies me to tell you about the tidal stream. My background is actually, my most recent background is actually in fuel cells. But it's fair to say that in 1999 I knew nothing about fuel cells. And if it wasn't for a conversation over a cup of coffee with a close friend of mine, I still wouldn't. And it was over that coffee we invented a new fuel cell, and within the next 7 or 8 years I became quite expert in fuel cell technology. So I left CMR a year or so ago to pursue a couple of other inventions. That's sort of square one, which is quite exciting, but my timing could be a little bit better, but to make you decisions. So here I was again a year ago, not knowing anything about tidal stream, but obviously very keen to explore the potential. And one of the benefits of not knowing much about something is you come in with fresh eyes, and you see things that maybe others have missed, and opportunities that maybe others have sort of walked past. And I think that's really how my new technology was invented through naivety, much the same way as my fuel cell technology was invented all those years ago. So, starting with the basics, we all know about the tide. We all know it's the sun, the moon, pulls the massive water around the Earth into two hills, effectively. When the sun and the moon work together, we get spring tides. When they decrease each other, we get neap tides. What's interesting is when these hills of water hit land masses or geographical features in the seabed, and here you get quite dramatic flows of water containing huge amounts of energy. If you can see there on this map of Wales, we've got a much muted estuary down at the bottom there, the Severn estuary. You see significant amounts of tidal flow around that area, but also up there at the tip over Anglesey, you see a very, very interesting area. Some of the tidal developers actually planning some stuff up there as we speak. So, in terms of the UK has some of the best tidal resources in the whole world. Some figures that Andrew quoted there. I chose a different set of data there. The Carbon Trust estimates that about 2.5 gigawatts of electricity generating capacity could come from tidal alone by 2020. And as Andrew mentioned, it's together with the potential from wave, that can account for about 3% of the country's energy. So some of the advantages we have with the tidal, which a lot of renewable energy sources don't have, is the fact that tides are very predictable. You can predict tides 10, 20 years in advance with a very high degree of reliability. What that means is that when that electricity comes onto the grid, it's known that, so it can become what the Greek refers to as a base load. The energy density of the tidal stream is very high. We're dealing with a very massive material moving pretty rapidly, and that holds quite a significant amount of energy. And that means that we don't need quite so large pieces of equipment. Also, the times of the tide actually stagger around the UK. So if we had tidal stream farms scattered around the coast of the UK, we could actually get power 24/7, which again helps with base load. I've already mentioned that the UK has some of the richest tidal resources, but one of the main features I think from all that man on the street is the fact that this has very low visual impact. Most of the hardware is actually under the water, so you could be looking out across your beautiful horizon of the seaside, and you wouldn't know it was there. Not like these wind farms. So The industry is quite an early stage, as Dan mentioned. But tidal in particular has quite a high potential for actually getting the cost of electricity down once some of these technologies have been better developed. So the key technical challenges, and I stress technical, there's a lot of commercial challenges as I was discovering, but the key technical ones are as follows. The main one is that we're putting hardware into some of the most aggressive environments on the planet. We've got these huge flows of water, massive forces that we have to cope with. And that has implications on the way that these devices are moored. But also, something that I hadn't appreciated in the early stages was electrical connectivity. We've been laying cables in the sea for many years now, but they tend to avoid laying cables in areas where there's high currents. The reason for that is that despite all the diagrams that you might see of tidal devices, the seabed isn't flat. It's hilly. In fact, where you have tidal streams, they tend to be quite a lot of valleys and when you lay a cable across that, often you get cables suspended over sort of chasm, and with a tidal stream flowing through that, sort of sprung. And within a matter of about 6 months, even the most armoured cable that you can get would actually wear through or fatigue stresses. Would cause it to have a break. So you can see if you want to have something like a power generation system which you don't want to touch for years and years, you have to be very, very careful how you lay your electrical cables to those devices, because they're up on the breaks today as you go. Another problem that a lot of tidal devices today have is uneven loading. Now, a lot of these devices, they tend to be sort of a bit like a windmill under the water, and they've got turbines about 15 metres in diameter, 16 actually, MCT, and they go into water depth of about 30 to 40 metres. So the bottom end of the tip, the turbine, is actually pretty close to the seabed. And if you look at the velocity profile of the tidal current, as you know, it sort of approaches the seabed, it's virtually static at the bottom, and it very quickly sort of ramps up to quite high speeds. So that means that in the swept area of the turbine blade, the bottom of that turbine is seeing very much less force than the top, and that creates an uneven loading on all the bearings and various components in the system, and also fatigue stressing the blades. This is quite a big problem that a lot of effort is going into sort of resolving. Another issue, of course, is abrasion. There's a lot of work also going into material specifications of blades to prevent them from getting worn out too quickly from the sands and silt and dirt that's carrying these currents. Another major problem is entanglement. People tend to sort of discard bits of old net and things like that out to sea. And these bits of net, they just sort of float around in the sea, subsurface. You wouldn't even know where they're on the surface, but quite often they'll get entangled in things like ship propellers and tidal stream devices, and can cause a lot of damage. Some of the biggest hazards actually are containers. They're often washed off the top of these container ships in high seas, and they're often sort of full of stuff which is heavy, so they tend to sort of sit like midstream in the sea. And so you're talking about something like a 40-ton mass of steel encased stuff that's just bobbing around subsea. And you imagine this thing hitting a turbine in a current that's about 5 meters a second. There's not actually much left of it. So this is a real problem for the industry. Less of a problem is barnacle growth. Wherever you've got light, which you tend to have in less depth of water, you get barnacles. And barnacles create drag on components and can actually change the efficiency of the device. Another thing that many of the developers out there haven't been really talking about, which is a significant problem, and one that could actually come and bite them in the arse later, and that's silting. Whenever you get a tidal stream or a wind stream, and you've got a turbine in front of it, it inevitably takes energy out of the flow, which is the point there, and causes the fluid behind it, whether it's air or water, to slow down. And in the case of water, if you've got a current that slows down and it's carrying sediment, it can actually deposit the sediment. And the result of that is that before and after your turbine, you get these big hills of sediment building up. And over time, those hills divert the flow away from your turbine, and you start losing efficiency again. So often they have to go in there and dredge it. And one of the big issues here, jumping straight down to installation and maintenance, is in a high-speed tidal current, there's only about an hour's window between each time where you can actually get in and do anything to these devices, whether it's dredging the seabed, whether it's taking the turbine up to replace blades or service bearings on the turbine, whatever. So everything has to be designed for quick and easy maintenance. And having something like silicon, for instance, is a real issue, because you can't go around and dredge an area in an hour. It takes days to do that sort of work. Another big issue, especially for the environmentalists, this is something that really sort of one of the bugbears of these environmentalists, which I do count myself as being one myself, but they want their cake and they want to eat it. They want green electricity, but they don't want to hurt the dolphins. They don't want to hurt the seals or the bats even, But you have to compromise somewhere down the line. I think we're probably causing a lot more damage by not having renewable energy than actually having it. And the research so far has shown that certainly in the case of tidal stream turbines, sea life in particular, tend to steer away from them anyway. They tend to treat them with a bit of curiosity, and once they get used to it, they just work their way around it. In terms of technology types, I've sort of surveyed the whole variety of different turbines out there, and you can split them up into a number of different sort of types. And this one is the sort of reactive turbine. And this essentially is the same as a wind turbine, but underwater. And we have two varieties of that. We've got the open free flow ones, which you can see there. One that most people have probably recognised as the marine, is the MCT one, which is actually gone out of the water now off the Irish coast. But also we have ones which have a duct around them. There's certain advantages in putting a duct around them that accelerates the flow and you get more kinetics, which obviously is easy to tap the energy out of that. The other type is a cross-flow system. Now the analogy here with wind is that this would be equivalent to a vertical turbine. Here we have hydrofoils which are arranged combine harvester type of style, and they sit on the flow and they move around in a similar manner. Again, you have a version there which has a duct built around it, again to increase its efficiency. This one's rather interesting and probably a little less developed. It's a reciprocating hydrofoil. And here it's sort of like it's building on how fish swim. Basically we've got a hydrofoil which can switch pitches at the end of each sort of sweep. So it sweeps backwards and forwards, changing its angle in much the same way as a fish's tail would. And the reciprocating motion is then translated into rotary motion and generate electricity. The final type is a green tide turbine. Now, it's fair to say that it's completely different to all the other turbines. It's simple. It has no gearbox. A lot of these other devices need gearboxes because the blades being 15, 16 metres in diameter actually turn quite slowly. And that results in the need for gearing up that speed to drive the generator quite moving fast. Ours doesn't need that. It's therefore very robust. But the key thing is it hasn't got any blades. So ask me how it's done, because pat's pending. I can't tell you. I would love to tell you. I get very enthusiastic about my technology. There's a number of people in this room who will tell you. What I can tell you is some of the advantages that it has. It has a much higher energy conversion efficiency. We estimate it's about 2.2 times more power you can get out of the tidal stream for a similar size device than a blade design. We can operate in much slower tidal strength, and this has significant advantages in that the way that the market's going to develop with the seabed is they can have a system like they do with oil exploration, where basically the seabed is actually rented, and there's an auction, and there's a lot of people wanting to develop on that seabed. There's a lot of competition, the price goes up. So when you go into a place where nobody else can go, the competition's not there, so you can get it for a song. So there's lots of commercial reasons why that's good. I've said before, we don't need a gearbox. This is one of the major areas where maintenance is required, and as I've mentioned before, maintenance and servicing is something that you want to avoid at all costs in this sort of environment. Similarly with blades, no blades to go wrong. There's no risk of damage through cavitation, which is a common cause of failure in a lot of these blade systems. And also another advantage of our system is we have very even loading of the turbine and bearings. We believe it's sea life friendly. We believe that sea life can actually pass through this without any damage at all. They might come out a little sort of dizzy, but essentially intact. Our design is designed for mass production and ease of installation and maintenance. I think it's fair to say that our technology promises to do to Type 3 what the jet engine did to aviation. Hidden flames. So, our strategy, well, competition is already getting established in the tidal stream space. There's a number of technologies that are already in the water generating small amounts of electricity, not much on the grid at the moment, but that's just around the corner. The UK government is soon going to be announcing that they'll be investing in tidal stream technology quite heavily. Unfortunately for me, that's mainly going to go into the more advanced technology. They're looking for a quick return on that investment. Inevitably, the size of this market is quite large. It's, to give you an idea of the scale of it, if we're to hit the 2020 targets and the full potential of tidal stream in that time, something like 32 turbines have to be built and installed per week in order to hit that target. Now, that's a lot of turbines. If you think that a turbine is literally the size of this room on one side to the other, that's a pretty large machine. So inevitably there's going to be a supply chain that builds to provide all different components into this industry. And our strategy is to be a tier 1 supplier in that supply network. And our device will be, basically we will be manufacturing and supplying a turbine generator unit, which is designed to fit onto the incumbent hardware of the winners of the race to tidal stream deployment. This has an advantage to us, which is it gives us lower R&D costs because we want to concentrate on our technology without having to invest a huge sums into developing more systems and servicing systems. It allows us to get quicker to market for similar reasons. But also, people that you could see as our competitors now are actually our customers. And also this gives us access to a retrofit market later on down the line once their existing hardware wears out. It's fair to say we're early stage, a little more than an idea, to be frank. We're getting a patent, we'll be on full patent by the end of this year. We have a business plan which is to support a research program that we are planning to through Cambridge University's Fluid Labs to prove the technology benefits and establish scientific credibility for the idea. And in order to find that, we're seeking funding. So any of you know anybody